One experiment changed physics forever. Just observing it made it behave differently. What the heck is going on? It's me and you're watching this channel. Here's how that experiment works and what it means for the way we understand reality. It's called the double-slit experiment, and it's been performed over and over again for about a century. The basic idea is that we fire one particle at a time through two very narrow slits in a barrier. The particles are small, like electrons or atoms or photons, the quantum mechanical stuff of the universe. And when they hit the barrier, they go through both slits at the same time. That's the weird part right there. They're tiny little particles, and yet they spread out like a wave and interfere with themselves. Sometimes they cancel out, and sometimes they add up to twice as much. That creates an interference pattern, just like the waves in the ocean do when they meet. This is all very unintuitive behavior, but the weirdness doesn't stop there. On the other side of the barrier, we have a detector that measures which slit the particle goes through. If we observe which slit the particle goes through, we get an interference pattern on the detector that looks like this. But if we don't measure which slit the particle goes through, we get an interference pattern that looks like this. The presence of observation literally changes the outcome of the experiment. How does that even make sense? There are lots of ways to set this up. Here's another one. We send our single photon toward the barrier. There's a 50% chance it goes through the top slit and a 50% chance it goes through the bottom slit. On the other side of the barrier, instead of an interference pattern, we see two dots where the photon hits the detector. Because we know that it went through one slit or the other, but we don't know which. Those two dots have a 50% chance of being the top and a 50% chance of being the bottom. So we can calculate that the overall pattern will look like this. But if we introduce an observation, a measurement device that lets us know which slit the photon goes through, then the interference pattern comes back. It's like the photons were playing dead. And then they saw us looking, and then they remembered that they were supposed to be dead, and then they died. That's not how any normal thing in the universe behaves. Now let's see what happens when we try to cheat the system. Suppose we split the difference between observation and no observation by putting an observation device at each slit, then we should get an interference pattern of the form. But that's not what we observe. Instead, we see this. What the heck is going on? How does an observation of an observation affect the outcome of the observation? The only possible explanation is that the act of observation affects the outcome of the experiment. You can call it the observer effect if you want, but that sounds too woo-woo. I prefer to think of it as the watcher effect because I'm not a physicist, and I do and play one on TV. If you've ever tried to take a photograph of a friend who's doing a magic trick, you may have noticed that when you point the camera at them, they suddenly can't make anything happen. That's because cameras detect light, and if you point a camera at something, you're making an observation that changes the outcome. You could say that the camera has a mind of its own, but really you're just saying that your observations are affecting the outcome of the experiment. That's what the watcher's effect is. It's just that, in the quantum world, the effect is far more dramatic. So why does this happen? Why do observations change the outcome? Well, that's actually a question that physicists still don't have an answer to. But there are some promising ideas. One of them goes something like this. When you make an observation of a quantum particle, you disturb it. It's like when you try to take a photograph of a hummingbird. It flies away before the picture is taken. So the act of observation pushes the particle into a different state. It collapses the wave function, as they say. I'll tell you what I think's going on here, but remember, I'm not a physicist. I play one on YouTube. When you make an observation of a quantum particle, you're actually creating an entanglement between yourself and the particle. That's because you're now in a state of knowing something about the particle. The particle is in a state of having been observed. If I toss a coin and it lands heads, I know something about the coin. It's that simple. If you're not making observations, you don't know anything about the particles. You can only ever know something about them after you've made an observation. An observation, by definition, is a measurement that gives you information about the thing you're observing. So if you make an observation of a quantum particle, you become entangled with the particle. That's what the collapse of the wave function is. It says the transition from a state of not knowing anything about the particle to a state of knowing something about the particle. It's the transition from a state of being unentangled to a state of being entangled. Here's another idea that I like. Quantum particles are both waves and particles. Waves carry energy. The energy of a wave is proportional to how big the wave is. So the bigger the wave, the more energy the particle has. So if you make an observation of a quantum particle, You're measuring how big the wave is. And the act of measurement changes the wave function because it changes the energy of the wave. In other words, the uncertainty principle. Heisenberg's uncertainty principle says that you and know exactly where a quantum particle is and how fast it's moving at the same time. The more precisely you measure one, the less precisely you can know the other. So if you make an observation of a quantum particle, you're disturbing it because you're changing the energy of the wave. Let's come back to the example with 2 dots on the detector. If we don't observe which slit the photon goes through, we get an interference pattern. If we do observe which slit the photon goes through, we get 2 dots. But if we put an observer at each slit, we get this weird pattern that looks like an interference pattern, but it's not. It's actually a pair of overlapping interference patterns. The photon goes through both slits at the same time. It's an interference pattern created by the wave function of the photon interfering with itself. But the moment you make an observation of the photon, you collapse the wave function. So the 2 interference patterns disappear, and you're left with 2 single-slit interference patterns. That's the Watcher's effect. I love this stuff, but I have to warn you, it gets weirder. For example, what happens if you make 2 observations of the same quantum particle? Does the wave function collapse twice? And if so, does that mean that the particle stops being a wave? Or does the particle stop existing altogether? Well, it turns out that if you make 2 observations of the same quantum particle, you create an entanglement between the 2 observations. In other words, the 2 observations become correlated. That's the essence of quantum entanglement. Einstein called it spooky action at a distance. But it's not actually that spooky once you understand how entanglement works. And you can understand how entanglement works if you watch this video. It's right here. Click on it. Go watch it. Come back here. We'll talk more about this stuff later. So why should you care about this Watcher's effect? Because it turns out that the Watcher's effect is everywhere. It's in the foundations of quantum mechanics. It's in the uncertainty principle. It's in Bell's theorem. It's in quantum computing. It's in quantum cryptography. It's in quantum teleportation. It's in quantum everything. And it's not just in physics. It's also in chemistry, biology, psychology, sociology, economics, politics, history, geography, art, music, literature, philosophy, religion. It's everywhere. The Watcher's effect is everywhere because the world is everywhere. And the world is quantum, and the world is also social. The social world is built on the idea of independent observers. We assume that we're all making observations independently of each other, but we're not. Our observations are all correlated. We're all watching the same show, and the show is changing our minds. That's the Watcher's effect. You might think that we're the ones in control, but we're not. We're just along for the ride. The quantum world is a strange world. In the quantum world, watching isn't passive. It changes the game. This is a channel, and now you know why. What do you think? Leave a comment below. I read them all. I'm here. See you next time.